Hello and welcome to my presentation. My name is Seyed Mohammad Mojtabaei and my collaborators were Dr. Jurgen Becque and Dr. Iman Hajirasouliha. The title of this presentation is Behavior and Design of Cold Form Steel Bolted Portal Frame Connections. As you know, cold form steel portal frames, moment resisting portal frames, are increasingly used in the construction practice, and the connections between the framing members are usually called apex connection, which is a connection between the rafters, and eaves connection, which connects the beam, connects the beam to the column. The aims of these project were to provide a better understanding of the structural performance of cold form steel bolted connections with varying design parameters, and also to propose a practical design equations to estimate the strength of these connections. The methodology that we have used in this study are as follows. Cold form steel bolted connections were simulated in Abacus by taking into account material nonlinearity, geometric imperfection, and realistic bearing behavior of the bolts. And also, finite element models were used in combination with Python script to investigate the effects of cross-sectional shape of the beam, the thickness, the bolt arrangement, and also bolt group length. And at the end, the results were employed to propose general design equations. The experimental work conducted by Lim and Nethercutt was used to basically validate our finite element models. Uh, Lim and Nethercutt conducted a 4-point bending test on the apex connection, and the beam element in this connection has back-to-back channel sections with the dimension as you can see in the picture, and 9 M16 bolts were used to connect the back-to-back channels to the gusset plate. And the difference between the connection test, actually they have conducted 4 different connection tests, and the difference between these connection tests was in terms of LB, which is the bolt group length. And it starts from 315 for the connection A to 615 millimeter for the connection D. For the bolt modeling, we have used simplified bolt modeling in Abacus, which is called fastener element. Actually, fastener elements make use of attachment points on each connected plate or selected surfaces, and attachment lines are created between these attachment points. And also, radius of influence are assigned to the attachment lines. It means that all degrees of freedom of the node within this radius of influence are coupled to the attachment points. And also the properties of these connectors are considered to be combined Cartesian and rotation. It means that we define the properties or the relationship between the relative displacement and relative rotation of the connected plate. The bearing behavior of the bolts against the channel web was obtained from double shear lab tests conducted by Lim and Nethercutt. Actually, as you can see in the picture, in the figure, load and the initial stiffness of the load elongation was incorporated as elastic bearing, and the rest of data was incorporated as a plastic bearing into the Abacus model. So we can, that's actually this load elongation will define uh, the relationship or the relative displacement between the connected plate, the relative displacement and rotation between the connected plate. For the element type, we have used general purpose S4R element, and the mesh size was 10 by 10 square millimeter. We have used bilinear material stress strain model, followed by a linear hardening range with a slope of E over 100. And for the boundary conditions can be seen into this picture. At the location of the load, the nodes in the cross section were coupled to the reference node, and the displacement was imposed to the basically to that reference point. And lateral restraints, similar to the experimental test, were provided at different locations. At the location of the load, at the supports, and also at the first line of the bolts in each connection. In addition, for the supports, the nodes in the S-end cross-sections were coupled to the reference node, and pin boundary conditions were applied to the reference node. To model the imperfection, we have used the results of elastic buckling analysis in Abacus. Actually, the first buckling mode shape obtained from the elastic buckling analysis were scaled and incorporated as a first model, as an initial shape of the imperfection. For the magnitude of imperfection, or that scale factor, we have used the results of Schaefer and Pecos and Walker studies. For the cross-section with the thickness less than 3 millimeter, Schaefer and Pecos recommended the values of 0.34 T and 0.94 T for the local and distortional imperfections, respectively, where T is the thickness of the beam. And for the larger thickness, larger than 3 millimeter, Walker proposed an equation to basically define the magnitude of friction. This figure shows, as you can see in the slide, this figure shows basically the behavior of the bolted connections, which was compared with the experimental results. And as you can see, the finite element results compare well with the experimental observation over the whole range of loading up to the peak load. And also, this table compared the results of the strength obtained from finite element analysis and the test. And as you can see, the average of the error between the test and finite element results is less than 2%. Is on average 2%, which is reasonable. For the parametric studies, the finite element model of the apex connection in 4-point bending was idealized as a cantilever beam with a bolted gusset plate connection subjected to pure bending moment. As you can see, the gusset plate between the back-to-back channels were fixed at one end, and the rotation was applied to the basically the other end of the beam. And also lateral restraints were imposed. Lateral restraints were imposed at the web edge. In addition, sensitivity analysis was conducted to determine the length of the beam. Based on the results, it can be seen that if we consider the length of the beam away from the connection zone larger and equal to 6H, H is the web depth. In this case, the capacity of the connection will not be sensitive to the beam length. In addition, in order to investigate the behavior and capacities of the connections subjected to axial compressive load, the same configuration as the moment connections was used. However, instead of applying pure rotation at the end, pure axial load was applied at the other end of the beam. And the selected design variable for the conformative bolted moment connections are as follows. We have considered different bolt group length starting from 0.5 to 3. Actually, it's the ratio of LB over H. LB is the length of the bolt and length of the bolt group, and H is the beam depth. It starts from 0.5 to 3 with the interval of 0.5, and the bolt group configuration was 2x2, 3x3, and 4x4. In addition, 5 different channels were used, back-to-back channels with different dimension, as you can see in the table, were used. And each channel in this back-to-back channel has got different eccentricities, which increases for the which actually starts from 11.11 for channel 1 to 33.33 for channel 5. The flexural and compressive capacities of cold-formed steel connections, which defined herein as MC and PC, are as follows. MC is equal to RM multiply MU, and PC is RP multiply PU. MU and PU are the cross-sectional flexural and compressive capacities of the connected members. It means the beam or the column element, which were obtained from finite element analysis. And Rm and Rp are the reduction factors, and these reduction factors accounts for the fact that local buckling, local web buckling adjacent to the connection may prevent the full cross-sectional flexural and compressive capacities, Mu and Pu, from being reached. And the reduction factors R were assumed to be a function of the selected variables, including the bolt group length, LB over H, the bolt group arrangement, and the channel geometry and thickness. In this table, the proposed reduction factor, the proposed equation for the reduction factors for the conformative bolted moment connection are listed. As you can see, the Rm is a function of T over X. T is the thickness of the element and beam element or column element, and X is the channel eccentricity. LB, and also the other function, the other parameter is LB over H, which is the length of the bolt group over the beam depth. And as you can see, the ratio of the Rm obtained from the equation over the Rm obtained from finite element is less than, basically the average of error is less than 1%. In addition, the similar equations were proposed for the compressive connections, and the terms LB over X and T over H can be seen in these equations as well. And the average of error between the finite element and the proposed equation is less than 1%. As an example, in this slide, we showed the proposed reduction factors Rm for the conformative bolted moment connection with rectangular 3x3 bolt configuration and various bolt group length and cross-sectional eccentricities. As you can see, 4 different figures are available for different beam thickness: 1 millimeter, 2 millimeter, 4 millimeter, and 6 millimeter. And also the finite element results are were shown in solid lines. However, the equation proposed in previous slide were shown in basically dotted lines. And as you can see, the results are in good agreement, and the general conclusion is that the connection capacity converges exponentially to the full cross-sectional capacities when the length of the bolt group is increased. And also the results indicate that the ultimate moment capacity of the cold-formed steel beam may be reduced by up to 40% for short bolt group length as a result of premature local buckling failure. The same similar actually figures was obtained for the cold-formed steel bolted compressive connections, and similar conclusions can be made as well. As you can see, they are exponentially varying. Okay, so what's happening into the short bolt group length and long bolt group length? For this purpose, we have extracted the elastic stress profile at the location at the end of the gusset plate, actually 1.5D away from the first bolt line, and for the LB over H equal to 0.5 and LB over H equal to 3. And the results, based on the results, we can see that the stress profile is significantly different in both cases. The longer bolt group this one, indicating in a stress profile which much more closely resembles the expected linear stress gradient predicted by the classic beam theory. However, for the short bolt group, the flanges in the channel with the shorter bolt group displays a stress gradient with the edges of the flange and the lip contributing very little in carrying stresses. Yeah, thank you very much.